So I'm going to review some of the material that I should have covered in more detail last week or the week before. So let's see, where shall I start? Maybe here. The electronics in this room, apart from being in the wrong place, still doesn't work. And, so I'm going to have to do this on the blackboard exclusively. So what I want to show you here is something that became apparent yesterday during the problem session, namely that some of these differential equations have singular points at infinity or at zero or at other points, and one needs to compensate for those singularities before applying the method of Frobenius. So, for example, Hermite's equation is y double prime plus lambda minus x squared y equal to 0, and the interval is from minus infinity to plus infinity, so already you have a singular interval. But the function q of x is lambda minus x squared, and so the criterion for a singularity at infinity is how this behaves if you replace x by 1 over z and then divide by z squared. And so this is lambda minus 1 over z squared divided by z squared. And now you look at this as z goes to 0. Well, obviously this is terrible at z equals 0. And so there's an essential singularity at x, absolute value x equal to infinity. And so one needs to compensate for that. The way you compensate for it is you look at the differential equation for very, very large values of x. Well, for large values of x, the equation is y double prime is x squared y. And a solution is y equals, an approximate solution is y equals e to the minus x squared over 2. Well, times some other thing. What did I call the other thing? H. I'll send you all a PDF of this. I've added 2 new examples to the, if there's ever a 3rd edition, there'll be 2 new examples in the 3rd edition. But I'll send you a PDF of these 2 new examples. So if you do that, then you find that the differential equation is x squared h double prime minus 2x cubed h prime plus lambda minus 1 x squared h equals 0. So now you can apply the method of Frobenius, and you see that p of x is equal to minus 2x squared, q of x is equal to lambda minus 1 x squared. Both vanish at x equal to 0, so the initial equation is simply r minus 1 equals 0, and one can set r equal to 0 or r equal to 1, and then apply the method of Frobenius. If you do that, what you find is, of course, this means that you're setting h of x equal to, for r equal to 0, it's just to sum an x to the n. And the form here, x squared h double prime, and extra x here, h prime, and then x squared h, the extra x squared at front, which looks kind of silly, actually serves a purpose because the two derivatives, h double prime, pull down two factors, two powers of x, and the prefactor x squared compensates for that. So the equation you get is a sum n minus 1 x to the n minus 2n x to the n plus 2 plus lambda minus 1 x to the n plus 2 a n equal to 0. And now what the easiest way to cope with this is to, on this sum, replace n by n plus 2. And if you do that, what you get is sum n plus 2, n plus 1, an plus 2 minus 2n plus 1 minus lambda an, all of this times x to the n plus 2 equals 0, and the coefficient of every power of x must vanish, and so you get the recursion relation an plus 2 is equal to 2n plus 1 minus lambda divided by n plus 2 n plus 1. And you can see that this is going to give you a series that in fact diverges, but even if it did converge, it wouldn't be a square integrable function. So you need lambda to equal 2n plus 1, and so these then give you the eigenvalues of the harmonic oscillator. And of course, they're a little disguised here because I wrote the original equation in really simple form, where all the units have been washed away and incorporated into the variable x and the parameter lambda. If you set n equal to 1, r equal to 1, what you get is lambda is equal to 2n plus 3. So this gives you, these give you the even solutions, and these give you the odd in x solutions, and the lowest solution is even, and so that's why when you set n equals 0, you get lambda equal to 3 here, so you skip the lowest order solution there. Let me now turn to a sort of prelude to the, in fact, this is a response to the question you asked during the problem session. The hydrogen atom, let's see, did I already write on this board? No, for some reason all right, so let me do the hydrogen atom case. The non-relativistic equation for the hydrogen atom is this. So, using a notation that makes the equation as mathematically simple as possible, we get this, where prime means derivative with respect to r. What you see is this has a regularly singular point at r equal to 0, but an essential singularity at r equal to infinity. And so here what you do is you first set big R equal to r to the L s, and then you look at this differential equation near r equals 0. And when you do that, you find that gamma is equal to minus L plus 1. Or equivalently, that L has to satisfy. This is gamma, not R. So. Wait, how to write a gamma so that it's clearly not an R. But anyway, gamma. Then to fix the singularity at infinity, you let S equal to e to the minus delta R times little s. And then you look at this differential equation near r equal to infinity. Well, near r equal to infinity, the important term is r squared r double prime plus alpha r squared r equals 0. So that's r squared r double prime plus alpha r squared r equals 0. You cancel the r squared and you see that r double prime, well, of course, r is equal to r to the L times this. The important derivative at the important aspect of this thing at r equal to infinity is the exponential. So this gives you delta squared r double prime plus alpha r is equal to 0. And I've got something actually wrong. Oh, okay. So delta is the square root of minus alpha. Right. So there's a typo here in my notes. I'll fix the typo before I send it to you. So that's basically how one does the method of Frobenius for cases where you have a singularity at r equal to 0 or r equal to infinity. Any questions about that? So basically what you have to do is you have to look at the equation near the singular points, approximate the equation near the singular points, and then solve it. And you solve it there in a very simple form near the singular points. Because in r equal to infinity or x equal to infinity, you eliminate all the terms in the differential equation that aren't huge at infinity, and at r equal to, when you look at, say, r equal to 0, you eliminate the terms that aren't huge at r equal to 0. Okay, now I'm going to switch to what I originally thought I'd cover today, which is, whoops, well, I guess I'll pull this back down. So I'm going to switch now to section 43 of chapter 7, namely the principle of least action. And so the action for a scalar field is an integral over all of space-time of some Lagrangian or Lagrange density. And the principle of least action, which, by the way, follows from the path integral formulation of quantum field theory, is that to first order, the variation in the action is 0, and here we're talking, of course, about variations, small variations of the field phi. And we can consider local variations. It's easiest to think of these as local variations because then you don't have to worry about any surface terms and you can partially integrate or integrate by parts and drop all the surface terms. So this change is the partial of Lagrangian with respect to the field times the change in the field plus the partial derivative of Lagrangian with respect to each of the space-time derivatives of the field times the change in the space-time derivative. I'm using A as an index that's 0, 1, 2, 3, 0 being time, 1, 2, 3 being space dimensions. I'm not using Greek letters because we're not Greek, and I think Latin indices just cause less traffic in the neurons. Now we're just varying the field so we don't have any other term here. Notice that I stopped on first derivatives. So here I'm talking about theories in which the action depends upon the fields and their first derivatives. One could consider a more general case. I'm not doing that. I'm considering this simpler case. Also, the change in the derivative is the derivative plus the derivative of the change minus the original derivative, so it's just this. And so this is equal to integral d fourth x partial L partial phi change in phi plus partial L partial dA phi times the eighth derivative of the change in phi. Now you see you integrate this by parts, drop the surface term because delta phi is local, and you get d fourth x partial L partial phi change in phi minus the eighth derivative of the partial of Lagrange density with respect to the eighth derivative of the field, and that's also multiplied by delta phi, so I can factor out the delta phi term. Delta phi is arbitrary. This has to be 0 for arbitrary small delta phi, so you can imagine delta phi is 0 everywhere except in a little pocket here and a little bump in space-time, and that means that at that point you have to have Lagrange's equations satisfied, which are the eighth derivative of the partial with respect to the eighth derivative of the field is the same thing as the partial of the Lagrange density with respect to the field. So these are Lagrange's equations. And this is called the principle of least action. More legitimately, it would be the principle of stationary action. And just to fill in that remark that I made about path integrals, what you have in a path integral is that the amplitude in Dirac notation to go from some initial field to some final field is an integral over all fields of e to the I times the action. And so what you can see, apart from some boundary terms, the boundary terms will be where this would be the final time. So T2, and this is T1, and we're integrating over all fields that go from T1 to T2. And so this is the amplitude to go from phi initial at T1 to phi final at T2. It's this path integral with this action, and so you can see that if this action varies only a little bit, if you have a path from phi initial to phi final that satisfies the classical equations, then this phase will be stationary. And if it's stationary, as you integrate over all fields and integrate over in particular paths that are close to the classical path, those paths will also contribute almost as much because the phase will be almost the same. So they'll be in phase and you'll have positive interference or positive reinforcement. On the other hand, if you consider an initial field and a final field and there's no classical path to go from one to the other, then this path integral will be much, much smaller. And so that's why, and by the way, this is divided by h bar. So these fluctuations are really important when the action is of the order of h bar as in quantum mechanics, but not so important when the action is very small. So for really microscopic processes, almost anything can happen. You don't need to satisfy the classical equations. That's why quantum mechanics, you have to use quantum mechanics or quantum field theory for processes that have very small length. Okay, well, Emmy Noether had something to say about symmetries in this case, and so the basic idea is the same as the one that I did for mechanics, namely that let's suppose that there is a change in the fields, delta phi I. So here I'm imagining that there are many fields. So if there are many fields, then, by the way, this equation looks like this. The partial of Lagrange density with respect to the 8th derivative of field I differentiated with respect to A is the partial of the Lagrange density with respect to the ith field. So if you have many scalar fields, you have that. If you have other fields, analogous equations occur, but they're not identically the same. So let's suppose you have some change in the fields that doesn't change the action density. Then that means that the sum over the fields of the partial of the Lagrange density with respect to phi I times the change in phi I plus the partial derivative with respect to the 8th derivative of phi I times the change in the 8th derivative of phi I, that this is 0. And so now you might be tempted to screw around with this term, but instead what I want to do is use Lagrange's equations to replace this with a sum on I of dA of partial L with respect to the 8th derivative, partial of Lagrange density with respect to the 8th derivative of the ith field. Delta phi I plus partial L partial dA phi I change, well, here we can commute the derivative. So we have the 8th derivative of the change in phi I. Now what Emmy Noether noted was that this is really a total derivative. And so this is the 8th derivative of the sum of partial L with respect to dA phi I times the change in phi I, summed over I. So that means that there's a current JA equal to a sum over the fields of the partial of the action density with respect to the 8th derivative of the ith field times the change in the ith field that leaves the action density invariant. And this is a conserved current. Conserved current because this equation here says that the 8th derivative of all that is 0 because of the symmetry. And so that means that dA JA equals 0. So this is really important in mechanics, and quantum mechanics and throughout physics, what we have here when we say dAJA equals 0, this means that it's the time derivative of the 0 component plus the divergence of the current equals 0. And so if you have some charge Q, which would be the integral of J0 over space, you see that the time derivative of Q is the integral of, I left out a D0. It's the integral of D0 J0 d cubed x, but that's minus the integral of the divergence of J d cubed x, and that's minus the integral of J dot ds integrated over the surface. So that means that the time derivative of the charge inside a certain volume is minus the flux of the charged stuff through the surface of the volume into the volume, which of course is what we mean by conservation of a quantity. We don't mean that it's conserved in every spatial volume. We mean that if it's not conserved, it's because something is going in around the volume. And so if you assume that nothing's happening in an infinity, then the time derivative of the integral over all of space should vanish, assuming there's no flux. So that's the basic idea of symmetries in field theory. So let's see. Let me write down what the J's are again. Namely, that JA is equal to the sum partial L partial dA phi I, change in phi I. But this thing here is actually defined as the momentum conjugate to the field. So in other words, the momentum conjugate to a field phi I is the partial with respect to the time derivative of phi I. And so in other words, the thing that's conserved with the density of the charge is J0, and that's a sum of partial L partial phi I dot times the change in phi I, which is the sum of the ith momentum times the change in the ith field. So it actually has a very simple form. Now that's, as I said, important in classical field theory, electrodynamics, general relativity, and it's important in quantum mechanics, gravity. Let me see what the time situation is. Does anybody have a question? Okay, I'm a little puzzled. I seem somehow to have gone through a great deal of material in only 35 minutes. So we've got like 45 minutes to discuss things, and I don't really have that much material left. Well, I guess I do, but I'm just surprised. Normally I run out of time rather than run out of material. Okay, so I guess I'll give an extra example of this. And I run out of blackboard space, so let's go to that blackboard for one example. One example is, suppose that we have n fields. So we have phi 1, phi 2, phi n. Boy, these blackboards are radical. as rough as the pavement in the middle of a street. Anyway, the action density then is a sum on I from 1 to n. It's a half phi I dot squared minus a half grad phi I squared minus a half mi squared. Oh, I want a symmetry though, so I need all the fields to have the same mass. Phi I squared, and I'm going to let the change in phi I be some small number times the sum on J of a matrix here that is anti-symmetric and real. So Aij is minus Aj. Then you can see that the change in L due to this change in phi I is minus epsilon times the sum of m squared phi I Aij phi j plus dA phi I Aij dA phi j. And this is 0 because of the anti-symmetry of the A's. And the charge then that's conserved, there are actually several of them. They're the sum, integral sum, phi I change in phi I, integrated over all space. And this is epsilon sum I, pi I, Aij, phi j, d cubed x. And this symmetry exists for any anti-symmetric matrix A that's real and anti-symmetric. And there's, of course, the group ON of orthogonal transformations, and there are n minus 1 over 2, if I counted correctly, anti-symmetric imaginary matrices. Well, you multiply them by I and they become real. And these are the matrices. These matrices then you have, in other words, for this Lagrange density, you have n minus 1 over 2 conserved quantities. This is an idea that's occurs in particle physics. The standard model, for example, has symmetries. In particular, the symmetry in question is various symmetries are an SU3 of color, an SU2 that acts on the left-hand fields, and a U1 of hypertron. So there are 3 symmetries. An action density that's invariant under space-time translations. Let's see, I may lose it on this board, so I'm going to go over this board over here. So let's suppose L is a function of the fields and their first derivatives, but in general it could have an x here. And we're going to say, no, we don't want that. We don't want that. We want L to be a function just of the fields and their first derivatives. So then the partial derivative with respect to the 8th coordinate is a sum on I, partial with respect to the field, partial of the field with respect to the 8th coordinate plus partial of L, partial to the 8th derivative, no, the Bth derivative of the ith field times the second partial derivative of that with respect to xa and with respect to xb. So that's the derivative there, and what we can then say is we can subtract this from both sides, and then what we get is 0 is the sum on I of, in fact, let me put a big bracket there, the Bth derivative. Oh, we use Lagrange's equation to replace this by the Bth derivative. So this is equal to the Bth derivative of the partial of L with respect to the Bth derivative of the ith field. By the way, these conservation laws, you notice I snuck in and used Lagrange's equation to get the conserved quantities. That means that the symmetry gets you conservation on the classical level. When the classical equations of motion are satisfied, it's not getting you symmetry on, it's not getting you conservation on the quantum level. And I must say, I've got to think about that. Does that mean that charge is not conserved microscopically? Well, as far as we know, charge is conserved to incredible experimental precision. It's enormously well studied. In any event, let's just go on with this and stay on the classical level. This is partial of the Lagrange density with respect to the Bth derivative of the ith field. Change the 8th derivative of the ith field plus partial with respect to the Bth derivative of the ith field, second derivative of the ith field with respect to xb, xa. So all of this, and then I've subtracted this from the other side. So that's all equal to 0. But now you can rewrite that as the Bth derivative of sum on I, partial L, partial Bth derivative of phi I, partial of the ith derivative, or let me just say the 8th derivative of the ith field, and then minus delta BA L to take care of the last term. So what we have is that this thing is conserved. This is called the energy momentum tensor. So we have TBA is sum on I partial of L with respect to the Bth derivative of the ith field times the 8th derivative of the ith field minus delta BA actual density. So this is the energy momentum tensor. Energy momentum tensor, and it has 0 divergence. The Bth derivative of TBA is 0. And so in particular, that means that the momentum PA inside a certain volume, which would be the integral, I'm just going to skip a step here. This is the momentum inside a volume. This is that momentum is minus the flux coming in, which is minus TKA d2s, integral over the surface of the momentum flowing in. In particular, since the pi i's are defined as the derivatives with respect to the time derivative of the I field, the Hamiltonian then, which is P0, it's an energy density, and it's, sorry, that's supposed to be T. T00, and this is a sum on I equals 1 to n of pi I dot minus L. So that's why, that's the form of the Hamiltonian. And for a scalar field in particular, a single scalar field, it is pi squared over 2 plus grad phi squared over 2 plus m squared over 2 phi squared. So that's the Hamiltonian for a single scalar field. That gives you the Klein-Gordon equation. I guess I have written down here. No, I just don't. Anyway, it's basically box plus or minus m squared acting on phi equals 0. And I say plus or minus because one has to have, well, all right, the actual thing is grad squared minus d0 squared plus m squared phi equals 0. So this pulls down e squared. This pulls down minus momentum squared. This is a minus m squared. So I would call this thing box minus m squared. Okay, so much for that. I'm now switching to a very different topic, namely nonlinear differential equations. And there are several examples here. Let me check the time to see how much time I have here. Okay, there are some examples. I think I'll skip the examples, or at least some of them. One is Riccati's equation, then there's an equidimensional equation, and then I have something about fluid mechanics and something about the speed of sound. These are worth reading. I encourage you to read them. But I think I'm going to skip and jump to the some nonlinear differential equations that occur in general relativity and cosmology. Cosmology, of course, has become much more relevant to physics with progress in observations from satellites and telescopes in space, and in particular the observations 40 or 50 years ago of the cosmic microwave background, and then more recently, about 20 years ago, observation of the acceleration of the expansion of the universe. We've known for maybe 50 or 70 years that, or 80 years, 90 years, that the universe is expanding since Hubble's observations. But in 1998, astronomers measured that expansion more carefully and realized that the expansion itself is accelerating. So all of these things are made. And then more recently, we have the observation of gravitational waves, something I thought would never be seen because the displacement of these mirrors is smaller than the radius of the proton. So out of the question measure what they did. Okay, so what is the invariant separation between two events? It's minus c squared dt squared plus something called a squared of t. This is the scale factor. dr squared over 1 minus kr squared over L squared plus r squared d theta squared plus r squared sine squared theta d theta squared. So now, for practical purposes, recent observations of the CMB, observations done with telescopes, indicate that either, K is a parameter that's either 0 or plus or minus 1. So, and where did this metric come from? Well, if you ask what is the most general metric of space-time that is maximally symmetric, why maximally spatially symmetric? Why maximally spatially symmetric? Well, when you look out with a telescope, you see that on the very largest scales, the universe seems to be homogeneous and isotropic. And in fact, that was revealed by the CMB observations over the past 20 years, because if you look at the CMBs, in particular that remarkable release last year, or actually it was 2013, I don't know if they've improved the image that much since then, but remarkable image of the sky, the microwave background of the sky is homogeneous to 1 part in 10 to the 5th, or 10 to the 4th at least. So that means that our metric should be spatially symmetric. Well, there are basically 3 spatially symmetric metrics, k equals 0, plus 1, minus 1. Observations indicate that k equals 0 as far as we know. And that means that either L is so huge we can ignore this term, or we can just set k equals 0. So you can basically forget about this term for practical purposes until you hear differently from the astronomers. This is the scale factor, which astronomers like to say that A0 is not the scale factor at time 0, but it's the present scale factor. My feeling is that astronomers use conventions that are completely backward from what we normally do, but, well, we've got to, I guess, respect some of their conventions. Anyway, so A0 is equal to 1. That means that when the CMB was first, when the photons of the CMB were first able to traverse space without scattering over off electrons, this happened about 380,000 years after the Big Bang, the hot Big Bang. I've forgotten what I was saying in that sentence. Somebody want to remind me what was I talking about?
You were talking about A0.
What?
You were talking about A0.
Thank you. That's exactly right. I was going to say that A, at 380,000 years after the Big Bang, was something like 1 over 1,000. So there's been an expansion of a factor of about 1,000, which means that those 1 degree photons are now 1,000th of a degree. And that corresponds to a temperature of 2.7 Kelvin. Anyway, if you take this metric, stick it into Einstein's equations, then what you find is 2 equations. A double dot over A is minus 4 pi big G over 3, the mass density plus 3 times the pressure over C squared. And the second equation is A dot over A squared is equal to 8 pi G over 3 rho minus C squared before, you can pretty much blow away that second term. These equations, of course, these equations become much simpler if you have an equation that relates P to rho. And if the material that's important at a given time is either radiation or matter or dark energy, then you can use a particular W in this equation to relate pressure to mass density. Mass density being, of course, energy density over c squared. So for W is equal to 1/3 for radiation, W is equal to 0 for matter, and that's because when we think of matter here, we're imagining matter as in the present universe or not too long ago when the galaxies are separated from each other by millions of light years, and consequently there's no pressure at all. Material particles are just too far away from each other to affect each other, except gravitationally. And for dark energy, W is -1. Now that W being -1 is quite interesting because it says the pressure is negative. And the reason the pressure is negative is that pressure is essentially minus the partial derivative of the energy with respect to the volume. And so if the energy, if it's dark energy, then the energy is associated with the volume. You double the volume, you've doubled the energy. And so this derivative is positive, and so pressure is negative. So if we substitute this equation in for P, then we get equations that are simpler. Namely, A double dot over A is minus 4 pi G 1 plus 3W over 3, A to the -3, 1 plus W. And that's quite a nice equation. And an even nicer equation is A dot over A squared is 8 pi G present density. Oh, by the way, this, where did I leave? I left out something. This is the present mass density, or density or effective mass density. So if it's radiation, you divide the energy density by c squared. If it's dark energy, you divide again by c squared. And what we have here then is A to the -3, 1 plus W minus c squared K over L squared, A squared. And as I said, you can blow away you can set K to 0 for practical purposes. And so let me check the time again, because I'd like to finish this chapter. Okay, I've got 15 minutes of this. Probably cover pretty much what's here. So what we can do now is look at particular cases for W. So one case is W equals -1. So this is just dark energy. And this means that we have a cosmological constant, and the cosmological constant then is 8 pi G times a rho 0. Now that rho 0, maybe I shouldn't have. All right, so I'm thinking of, well, anyway, this is sort of an unrealistic example. Let's just take this to be the present density of dark energy. Then this could be positive or negative, and the equations then are simply A double dot over A is 8 pi G rho 0 over 3. So that's a pretty simple equation to solve. And the other one is A dot squared pi g rho 0 over 3a squared minus c squared k over L squared. Now, I said you can forget that last one. So if you set k equals 0, this thing is trivial to solve. And so let me see what I did in this example. So one case can be that the energy density, the dark energy, has a negative density. This would be the case for k equal to -1. And then what you have is a double dot is minus lambda squared a. So a is equal to, let me just jump to the solution, c over L lambda sine lambda t. And what is little lambda? Yeah, little lambda squared is 8 pi g over 8 pi g absolute value of 0 over 3. Okay, so that's these are, this is a de Sitter, this is called a de Sitter space, or de Sitter space-time. And for negative dark energy, k can't be 0 and k can't be 1. So this is kind of unrealistic. As I said, k equals 0 as far as we know. If we now go to lambda, which again is 8 pi g dark energy density positive, which is what we actually have, and then we have a double dot equals lambda squared a, and the solutions are a of t is equal to c over L lambda cosh lambda t. This is for k equals 1. The realistic case is a0 e to the plus or minus lambda t, k equals 0, and c over L lambda sinh lambda t, k equals -1. So these are the other de Sitter spaces. And I plotted them in figure 7.4, and just to, over here I have absolute value of a of t, because you can see that a, the scale factor, comes in only as it's square, so the sign of a doesn't matter. And so if we have time in gigayears, then with minus 100 here and plus 100 here, what we've got are various possibilities. One is this dashed thing, another one is this, and then a third is this bouncing type case. And so let me just, let's see, which one is de Sitter and which are anti-de Sitter? Okay, the anti-de Sitter are these guys up here. These are the anti-de Sitter cases. And the So the dotted one, this is anti-de Sitter. So this is the one that's probably ruled out because k equals 0 isn't a possibility. What we've got left then are these two. And what's interesting is that for large times, this is a pretty good approximation to the actual universe. In other words, right now, the energy density of space is about 2/3 dark energy. And in another 10 billion years or so, it'll be, I don't know, 90% dark energy. And after a while, you see the energy density of matter goes as 1/a². In fact, I can write it as the energy density of matter now divided by a³. And so you double a from the present value, it goes down by a factor of 8. You double again, you're down by a factor of 64, I guess, or am I just after a while, so this is a fairly good approximation. And in fact, what appeals to me about this is that some people, one guy at Princeton named Paul Steinhardt, and a guy at Harvard named, I forget his name, I'm not perfect with names. Anyway, have proposed the universe actually is a bouncing universe. That this hot Big Bang occurred when the previous universe came together and came out. And this is sort of an alternative to inflation, because it explains the hot Big Bang and the uniformity as arising from the collapse of a universe. And so you take a universe and squash it all together, well, it's going to be essentially homogeneous when it expands. So that's the case for de Sitter. The other cases are a universe of radiation. So here we have W equal to 1/3. Now, the universe of radiation, that's actually a good approximation to our universe for the first 50,000 years. First 50,000 years, the radiation dominated matter, and of course dark energy, being the energy of the vacuum, was Zippo because the universe, the space, was so much smaller. And the reason why radiation is important is that the density of radiation goes as the present density divided by 8⁴. And so as you go to early times when A is small, it's going up by 8⁴. So that's why it was dominant for the first 50,000 years. The equations then are a³ A double dot is minus 8 pi g rho 0 over 3, and a dot squared is 8 pi g rho 0 over 3a squared minus c squared k over l squared. And again, you can drop the last term for practical purposes. And so these are simple equations to solve, and I'm looking for the k equals 0 solutions for this. The k equals 0 solution is very simple. It's a of t is equal to r times the square root of t, where r to the 4th is equal to 32 pi big G rho 0 over 3. Here I'm assuming that I guess that a of 0 is 0. So that, and I'm going to skip the k equals 1, k equals minus 1 solution. They're written there in the book, but I don't think it's important. What is interesting is that if k is equal to 1, then the universe reaches a maximum size and then collapses. Even though it's nothing but radiation, it reaches a maximum size and then collapses. The universe of matter, on the other hand, has these equations. A squared A double dot is equal to minus 4 pi big G rho 0 over 3. A dot squared equals 8 pi g over 3 rho 0, 1 over a minus c squared k over l squared. As I said, you can blow away the last two. So the first order solution, let me write that down. For k equals 0, this is just some m t to the 2/3, and m cubed is 6 pi g rho 0 is positive. So this is a matter universe. So the matter universe expands as t to the 2/3, and the dominant component of the energy of the universe was the energy density of the universe. Between 50,000 years and 10 billion years was matter. After 10 billion years, the dominant component was of the energy density was dark energy, which presumably is simply the energy density of empty space. And in quantum field theory, you expect that the ground state of the theory has an energy or an energy density, and that could be essentially anything. And in fact, if you have a soluble, simple quantum field theory, the answer you get is minus infinity or plus infinity. And you get minus infinity theory of fermions, you get plus infinity theory of bosons. A long time ago, Pauli suggested that these two could cancel, and in fact, in theories with supersymmetry, you do have cancellation. If you have exact supersymmetry, cancellation is complete. Because as far as we know, there's been no evidence experimentally for supersymmetry. Let's see, I guess we're done with that. One might look at one last topic here. What do you have for time? Do you know what time it is? 6:42. All right, 3 minutes. Let's look at a single field theory, classical or quantum, phi dot squared minus, let's look at one in one space, one time dimension. So the potential energy is V. This is the, instead of grad phi squared, we just have the first derivative squared. The Klein-Gordon equation dV d5. It turns out that if, let me see, what did I say V was? Well, in general, we can integrate this. If we assume a special form for the equation, let's suppose that phi of x and t, or t and x, is actually phi of x minus vt. So we've got a traveling wave solution. Then this equation turns, then what we can say is phi dot is minus v times the youth derivative, or just the derivative of this with respect to u. And then the equation, the Klein-Gordon equation, is 1 minus v squared. The double youth derivative is the phi derivative of v, and then you can integrate that, and the integral is, well, you find u minus u0 is equal to an integral square root of 1 minus v squared, that's just a constant, over the square root of 2 e plus v of phi d phi. And in particular, if v is phi to the 4th, in the sense of, so let me say what I mean by phi to the 4th. I mean lambda squared over 2 squared minus phi 0 squared squared. This is kind of like a Higgs potential in one dimension. You can find what U is exactly. U minus U0 is minus or plus square root 1 minus V squared over lambda phi 0. Inverse hyperbolic tangent of B over B0. And that looks like, I had a picture, oh yeah. So it basically looks like this. So all the energy is at a particular point in space-time. It's where the field goes from a negative constant value to a positive constant value, and it jumps in this way. All right, so we're done with differential equations. I will start the next chapter on in the next lecture. And I'm going to do the chapter on integral equations very, very quickly. I'm just going to basically define what integral equations are and mention a few things about them. And then we'll go on to Legendre polynomials and Bessel functions. And I think we'll have time to finish both of those chapters. Any questions? Anybody starving and need a candy? One person. Okay, let me throw you a candy.